Hello Triple students, we are moving on to some physics today. So we're going to start looking at the Physics Paper 2 and we're going to be looking at the solar system. So this kind of helps if you which you all did waves last year in your trilogy lessons. So we're just going to do an overview for the first lesson on the space topic about our solar system. Now, in case you weren't aware, the word solar means to do with sun and system means via organisation. So there's the sun. Okay, and these are planets that orbit them. So we would say that we live in a heliocentric system. Okay, so that helios is Latin for sun. So we live in a solar system, etc. So we're going to look at the sizes and shapes of things. That one's quite famous. Saturn there. Let's go. Okay, so the first thing we're going to do is we're going to list the planets in our solar system in order of the sun. So pause it if you can do it, but we've got Mercury, Venus, Earth, Mars, Jupiter, asteroid belt in between those, and then we've got Saturn, Uranus, Neptune, and Pluto. I'm going to put in brackets because it's a dwarf planet. Other things that you can find in our solar system, rocks, and then we go into the world of asteroids, comets, meteors, comets being balls of rock. We've got gas, we've got planets. We've got, we don't have stars in our solar system. We have one star. We also will have moons and different satellites as well. That'll probably do. Okay, this is just to show you what you need to be able to do. So obviously we're all aiming for this end of the spectrum. This is the minimum. So you need to talk about gravitational forces and how that helps with the solar system being made. You need to describe the variety of objects, so moons, planets, the formation of protostars and planets, so the rocks and the pressure forming protostars, analyze data comparing the composition, so what they are made from, and why a star is in main sequence has a constant radius. So this is about the chemical reactions and the chemical reactions in terms of the nuclear fusion, but also the physics in terms of the gravitational forces. Let's go. Okay. Ignore this map, I stole this. So where are we now? Well, you're all at your homes, so you would maybe start with your home address. I've just started with the fact that I am in Sevenoaks in Kent in the southeast of England, which is on Earth. Just going to get rid of that. Probably shouldn't put across to Earth. Might be misconstrued. The solar systems. The Earth is within our solar system, so we are there, the third rock from the sun, which was a popular TV show in the 90s. We sit on Orion's arm of the Milky Way, which is I'm just going to get rid of that arrow because that's now misleading. The Milky Way is the name of our galaxy, and our galaxy is part of a local group or a local cluster of galaxies. The one that is most similar to ours is Andromeda, and that's our closest galaxy. And we are part of the Virgo supercluster of galaxies. And that makes up the universe. So universes are made up of superclusters of galaxies, which are made up of clusters of galaxies, which are made up of local groups of galaxies. Then within each galaxy, you have parts of the galaxy, and galaxies are made up of clusters of solar systems, and solar systems are made up of planets orbiting the sun, and planets have countries on them, defined by land masses, and those countries are separated into regions. Kent, and those regions are separated into towns, villages and cities. The universe is enormous, so I mean in terms of trying to scale it, if you wanted to look across our galaxy, so if you wanted to know what was on this side of the galaxy over here and we're on this side of the galaxy over here, it would take light so long to reach where we were looking and back again. We would be probably looking at the prehistoric era. That's how long it would take. So when we look at from planet Earth, I'm not sure where Earth is. 1, 2, that's not right because that's red. So let's just say we're here for the sake of argument. When we look at the sun, we are looking at the sun 8 minutes ago because it takes light 8 minutes to travel there and back so we can see it. So here is the sun. And the sun is a star, and that star is in main sequence. Okay, so it's in the main sequence of its life. When that main sequence over, well, life will be over, which will be sad and awkward. Okay, so the first planet is Mercury. Oh, here we go. I'm going to correct myself. Venus, Earth, name the country, well, the continent, that was a continent. Mars, asteroid belt, Jupiter is good. I got it right. Oh, Uranus. I put Neptune before Uranus. Neptune. Okay, so our solar system consists of 8 planets. Obviously, we have got that ninth that is Pluto. There's Pluto down there. Pluto is a dwarf planet and it keeps changing in terms of its definition. So let's have a look at the other things that can be found in the solar system. Add the planets and you can colour them in. You can just draw this yourself if you want to. Try and explain why the closest planet to the sun are made of rock and the ones furthest away are made of gas. See if you can consider that. I'll give you a clue. It's to do with physics. So how is the solar system formed? So we need to go back about 4.6 billion years, so just a bit younger than when the Big Bang happened. And we know the Big Bang was when all matter started from one single point and there was a big explosion and it all started moving outwards. And that's why the universe is expanding. So let's look at the history of our planet in comparison to this. So the Big Bang happened, and this I love this. So this is the cosmic calendar. So if we were to put the cosmic calendar, if we were to say, okay, if in January was when the Big Bang happens, and February, March, and April is where solar systems are forming. May is when our solar system forms. May is when our solar system forms. September is where planets are forming. And then October is when life is starting on Earth. Now, if you remember from this part, this happened about 3 million years ago, 3 billion years ago, 3 billion years ago. And then eukaryotic cells are happening 2 billion years ago. And that means that modern life on Earth would have started from December. And then we've got all this kind of evolution. So humans wouldn't have evolved until 8 minutes to midnight in December, which is amazing. Which means that, like, if we spread down the last 60 seconds on Earth, World War II would be 0.2 seconds, 2 seconds. Ago. On this scale, the solar system was created around September, so our solar system wasn't created until. Okay, heavy elements like uranium exist because of a star going supernova. So we're going to look through the life cycle of a star. What is important to note is that all of the most simplest or the most abundant element in the universe is hydrogen, and when it reacts under great force, it will make a helium nuclei. And if helium and helium reacts, it makes a boron nuclei. If helium and hydrogen form together, it will make a lithium nuclei. And so if you get larger and larger and larger and larger elements being forced together under extreme pressure, that's where you get these big elements. So what we know is that all of the elements in your human body come from the creation of stars. So you are made of stardust. Isn't that lovely? Oh. This is obviously terrible chemistry, but never mind. So we're going to talk about the life cycle of a star briefly, and then we're going to do that in more detail later on. Okay, so somewhere in the universe there would have been clouds of dust and gas. And all stars form when they're pulled together by gravitational friction. So this is a cloud of dust here, and this is called a nebula. And that was joined together by the forces of gravity forcing that dust and gas together. Once they're pulled closer together, this increases their kinetic energy. So they've got loads of energy and they're moving towards each other, and they start to merge and then they start to spin. And they become more concentrated, and this is called a protostar. As it gets bigger, it gets even more kinetic energy, lots of collisions, so lots of chemical reactions. So then it gets hotter, and if particles have enough energy to collide, they will start forming new nuclei and sticking together under that pressure, and we get nuclear fusion. So nuclear means of the nucleus, fusion means joined together. So this literally means the nuclei of atoms fuse. And the reason why it needs to be hot and have a lot of pressure is because if you remember the nucleus of an atom, so here's a picture of an atom, the nuclei are positive. And so if you've got positive and positive coming towards each other, they naturally want to repel each other, positive and positive. So you have to put them under huge amounts of force to get them to join together. Okay, so the protostar attracts smaller objects not big enough to become stars. So like Jupiter could have become a star, but it was a bit too small. They begin to orbit the star. So we've got the star in the middle here, and then you've got other things starting to just sort of move around it because of this gravitational pull. In the middle of the star during this time, and this is happening in our sun right now, we have got nuclear fusion, and we're going to go into this in more detail as well. So here's nuclear fusion. I've got deuterium, which is an isotope of hydrogen, and tritium, which is also an isotope of hydrogen. And I know it's hydrogen because it's got one proton, and all hydrogen has one proton, but it has got two more. This has got two neutrons and this has got one neutron, so they're different isotopes, but they're the same element, and they will join together, make helium, and they will give out loads and loads and loads and loads and loads of energy. And all life on Earth requires the sun's energy, light energy, heat energy, etc. And in our sun, it produces up to iron doing that right now. So our sun is like this. It's in main sequence. So it means that during this time that we have got gravity causing this pulling in motion, and that is causing nuclear fusion, which causes energy and pressure to be released outwards. And because these two things are in balance, the sun roughly stays the same size. Oh, there's a much better diagram. Taking away all my ramblings, I'll get rid of those. Okay, so the outwards arrow is going to be our fusion reaction giving out energy, and our inwards is going to become gravity. So as our solar system is now, the ball of gas collapsed and concentrated together, it spins, brings clumps of rocks together, and they become bigger and bigger. Close enough to the star, all gas uses out its formation, leaving bits of rock to make rocky planets. Further out, leftover gas joins to make planets and gas giants in many solar forms, and then this is why all the planets further away are basically gas, and all the ones closer are rock, is because it's just got more gravitational pull. Okay, this is a sheet I'm going to attach onto here. If you haven't got this in front of you, you might want to just draw the diagrams, and then you can sort of summarise the points that are on there. But you have got to complete the diagrams with the following words. So I'm going to go through each diagram, add some words that we could add on there. And then you can pause the video and you can write it down if you haven't got the sheet. Okay, so the first one has got... clouds of dust or rock exist in a planetary nebula, so we can label on their planetary nebula, and they will be rotating, obviously because of the gravity pulling inwards. There's going to be a rotation going in this direction. So let me just tick off those two words: planetary nebula, cloud of dust and gas. Rotation's not even on here, but well done. You could also label it gas because there is another mark on there. And then we get the protostar being created, which is a disk of rotation, and you need to label that up on there. And then number 3, when the protostar becomes hot enough, hydrogen atoms start to fuse, and that's nuclear fusion. I'm just going to add nuclear on here. And this is where we actually have a star being formed when nuclear fusion is happening. You might also want to add on here that the temperature is increasing. One of the pet peeves is when people write temp. Please don't do that, because you will get no marks in the exam. So the temperature is increasing. And then we've got the formation of the solar system. The sun is the star in the centre. The heat from the sun evaporates everywhere. the sun evaporates any ice in the cloud and pushes away the gas, leaving clumps of rock orbiting. So we've got rock on there, we've got gas here, the sun here, and we've got radiation, heat radiation being given out. And you could also, if you wanted to, add in fusion is happening there. And then these are the majority of the labels that you need to add onto your diagram. So you need to add the asteroid belt, you need to add Mercury and Earth and Venus and Mars, etc. So that you have to just sort of count. So this is in the first loop, so that's Mercury. Venus is in the second loop, or elliptical. We call it an elliptical shape. And then down here, this is our main sequence star that we've got now. So we've got the gravity pulling in and the radiation from the, radiation from the nuclear fusion. Don't know